So as you saw in our introduction there, we cover some topics in here that are relatively simple. Two reasons for that. One is when we get to the more difficult stuff, like the basic algebra that we cover in here, I have found that a lot of the problems people have come from the fact that they don't really understand what we're doing in the very basics. You may be very good at doing it, but you don't know why we're doing it. And that's something you need to know to understand algebra, to truly understand algebra. The other thing is, I try to approach things a little bit differently. Like I said, I want you to know why you're doing things, because that's the key to problem solving is not just knowing how to solve a problem, it's knowing why you're solving it. So when you find a problem that's a little bit different, you know what to adjust to solve that problem. So we're going to start off today with just a quick little review of a couple of very basic math topics. The first one being the most basic, but also probably the most misunderstood topic in math. And that is, what is a number? If I put a 4 up there, how many of you, show of hands, would say that that's a number? Most people would, right? Well, really, that is just a numeral. It is an amount. It's telling us how many of something. To truly be a number, we have to have that amount, but we also need to know of what. So let's say it's 4 cows. So we have the 4, which tells us how many. I'm going to call that the count. But then we have the cows that tell us of what. And that's, what's that? The value? Well, I'll refer to it as the name. It could be a label, whatever, units or whatever. Now, you might be thinking, oh no, another one of those teachers is going to require us to label everything. That's not my purpose of pointing this out. I'm not going to be really strict if you forget to put inches or feet or whatever on your answers. But knowing about the two parts of a number and being aware of them explains why we do things the way we do in most of our basic math operations. So to illustrate that, let's take a look at our two most basic math operations. Addition and multiplication. Now some of you might be wondering, where did subtraction and division go? Well, if you get really deep into number theory and math theory, there is only addition and multiplication. Subtraction and division are parts of, subtraction is part of addition and division is part of multiplication. One way to think of it is subtraction is just addition done in reverse. Now in here we're still going to do subtraction. I'm not going to get that technical that we eliminate it. But there are going to be some cases where we convert subtraction back into addition, so it simplifies some of our problems. So any rules that we state that apply to addition also apply to subtraction. And the same with our multiplication and division. Any rules that apply for multiplication also apply to division, because they're really kind of the same operation. So let's do an example here. Let's say I'm going to take 4 inches plus 7 inches. What's my result? 11 inches. Not terribly groundbreaking there, right? But let's take a look at what happened with our count and our name. Our counts, we had 4 and 7. What happened to those? Yeah, they added together to make 11. We combine them. We're adding, so we combine them with addition. So we combine the counts. If we look at what happened to our names, we had inches, and it stayed inches, right? So when we add numbers, we combine the counts, but we just keep the name. When we multiply, let's look at 4 inches times 7 inches. What do we get? 28 what? Not inches, but inches squared. If you think about it, if we're multiplying two dimensions, it's generally looking at a rectangle or an area of some sort. So you're doing 4 inches times 7 inches, you're going to get inches squared or square inches in area. So let's look at what happened there with the count and the name. Our counts are still 4 and 7. They became 28. We still combined them. It's just this time we're multiplying, so we combined them with multiplication. So we still combine the counts. The difference here is what happened with the names. We had inches and inches, and it became inches squared. So when we multiply, we also combine the names. So when we were adding, we combine the counts and we just keep the same name. When we're multiplying, we combine the counts and we also combine the names. And again, that may not seem like a big deal. But when we look at our other forms of numbers, that describes all those rules that we were told were special for each different form. It actually explains where each of those rules came from. And we'll look at that a little bit here today before we're done. The other thing it does is it actually tells us what numbers can even be used in each operation. For example, let's say we have our 4 cows plus 5 boys. Does that give us 9 cowboys? Yeah, it don't work that way, does it? Let's say we did it the other way around. Let's say we got 5 boys plus 4 cows. Does that give us 9 boy cows? No. Anybody in here with a farming background? So you can tell me that this is a whole bunch of bull, right? Okay, long way to go for a joke. But anyway, there's a point behind it. I'm a math teacher, by the way, which means I'm required to have a stupid sense of humor. There's a point behind that joke, though. When we add numbers, we're going to keep the same name, which implies that we have to start out with the same name. We added inches and inches. We kept it as inches. Here, we don't have the same name. We don't know which one to keep, so we cannot combine those with addition or subtraction. 4 cows and 5 boys is just 4 cows and 5 boys. Now, a little bit more practical example of that might be, what if we had 5 feet plus 2 pounds? What do we get? We get 5 feet and 2 pounds. They have different names. We cannot combine them with addition or subtraction. However, for multiplication, if I had 5 feet times 2 pounds, when I multiply, I'm going to combine counts. So 5 times 2 is 10. But I'm also going to combine the names. Feet times pounds is just foot-pounds. It's a unit of torque, or if you're looking at construction, it's a unit of bending moment in a beam. So when I multiply, because I'm going to also combine the names, I do not have to start with the same name. So now that we've got that out of the way, let's take a look at how this affects us in some of our other forms of numbers. Let's look at everybody's favorite, fractions. Yeah, I caught some of the looks. I realized that if I asked people on their way in the door what they hate most or what they struggle with most in math, 4 out of 5 people would say fractions. 5 out of 4? So, just a little review. The top number is called the, careful, numerator. On the right track. The bottom number is the denominator. There you go. So I'll pause there, reminding me I should warn you. I'm a horrible speller. A lot of times I'll get halfway through the word and forget how to spell it. I also realize my handwriting leaves something to be desired, especially later in the afternoon when I'm tired. If anything ever appears up there that you can't read, I assure you it was intended to be in English. Either I butchered the spelling or my handwriting's too sloppy. I will not be offended if you ask me what something says, so please do if you can't read it. So what do those mean, numerator and denominator? Well, numerator, to numerate. Every 10 years, our government sends out people to do the census, to numerate the population. What are they doing? They're counting. A numerator is a count. Denominator, we have different denominations of money, different denominations of organizations, of church groups. To denominate means to classify or to give a name. So those two parts, the 4 and the 7, numerator and denominator, are just a count and a name. A lot of people look at a fraction and they see two numbers, but it's not. It's a single number with our standard two parts. We have 4 of something. Just like having 4 inches or 4 cows, here we have 4 sevenths. So the 7 isn't really a number, it's a name. So with that in mind, our basic addition or subtraction of fractions. If you think way back to 3rd grade, when you first started doing operations with fractions, that 3rd grade teacher said to add fractions, you must have common denominator. There you go. That's not a special rule for fractions. When we add any numbers, we must have the same name. When you add fractions, you combine numerators. 4 plus 2 is 6, and you keep the common denominator. Again, that's not just because your 3rd grade teacher said so. It's not a special rule for fractions. That's how we add any number. We combine the counts, and we keep the same name. So if I had 1/3 plus 2/5, can we add those the way they're written? No, because right now they have different names. When we look at fractions in more detail, we'll go over how do we change those names. But for now, we just need to know they're different. What if I had 4 sevenths times 2 sevenths? How are we taught to multiply? Just go straight across, right? 4 times 2 is 8. 7 times 7 is 49. Why? 3rd grade teacher said so, right? Well, the reason why is because that's how we multiply any numbers. We combine the counts, and then we also combine the names. So if I looked at my 1/3 and 2/5, do I need the same common denominator to multiply? No. Again, that's nothing special for fractions. Anytime we multiply numbers, we do not need the same name. We're just going to combine the counts. 1 times 2 is 2. And then also combine the names. 3 times 5 is 15. Let's look at decimals. 0.21. The formal way of pronouncing that is 21 hundredths. Good. And when we write it out that way, it's more apparent what the count and the name is. We have a count and we have a name. So let's try to add some decimals here. Let's take 0.21 plus 0.3. So if I set that up, is that going to work there? Why not? Okay, what are we supposed to do? What were we told to do when we add decimals? Line up the decimal points, yes. And the reason for that is exactly what you said right there. They don't have the same name. This is 21 hundredths. This is just 3/10. They have different names. But if we just put a 0 there, now this becomes 30 hundredths. So now if there's a 0 there, the decimal points automatically line up. Lining up the decimal points when we add or subtract decimals is nothing more than making sure they have the same name. Then we add them. We got 21 and 30 is 51. Where's my decimal point go? We bring it straight down. Again, 21 hundredths plus 30 hundredths better be 51 hundredths. When we add, we keep the same name. Bringing the decimal point straight down is just keeping the same name. So those special rules for adding decimals are not special. They're the same rules for adding any other number. So if we go to multiply, do I need to line up my decimal points? No. Why not? Because when I multiply, I don't need the same name. 21 times 3 is 63. Where's my decimal point going to go? It doesn't go right in front of it. I got to put a 0 there, then my decimal point. Why? We were taught to count 1, 2, 3 decimal places in the problem, 1, 2, 3 decimal places in the answer, right? Why? Third grade teacher said so. Well, it goes back to the same rules as all of our other multiplications. 21 times 3 is 63. But this is hundredths, and this is tenths. Tenths times hundredths, or hundredths times tenths, is thousandths. So when we're counting those decimal places in the problem and making sure we get that many decimal places in the answer, all we're doing is combining the names. Well, while we're on a roll, let's look at that. Algebraic numbers. Some people get a little squeamish when we put the variables in there. But this is nothing different than any other number. We have a count, the 4, and we have a name, the x. It's just like having 4 inches or 4 cows or 4 sevenths. Here we have 4 x's. The difference is we don't know what an x is, and we know what all that other stuff is. But it really doesn't matter. It behaves exactly the same way. 4x plus 11x is going to give us 15x. Good. When we add numbers, we combine the counts. 4 and 11 make 15, and we keep the same name. Yes, sir?
But how can a name make the product become bigger? You know what I'm saying? What if it's like x is like 3?
Well, if we know what x is, then we put the value in there.
But then it's no longer a name, is it?
Then it's no longer a name. We've now replaced it and turned it into a different type of problem. Yes.
Oh, so
Well,
just how they're set up is it's a name.
yes.
So it's like a name slash numeral?
Well, it's a variable can take on many different roles. It can be a placeholder where it's waiting for a value to come in. It can be an unknown where it has a value. You just have to figure out what that value is. And there's several different roles it can take on.
Sometimes it doesn't have a role. Right?
Yeah. So how about if we had something like 5x plus 2y? What do we get? 5x and 2y, yeah. Just like up here where we had 5 feet and 2 pounds, we can't combine them with addition or subtraction because they have different names. 5x and 2y have different names. So what if I have 4x times 11x? Well, I combine the count still. 4 times 11 is 44. Now, just like inches times inches became inches squared, x times x is x squared. Good. What about my 5x times 2y? Perfect. 10xy. I combine my counts. 5 times 2 is 10. And then just like feet times pounds became foot pounds, x times y becomes xy. The exact same rules that we use for whole numbers. Just looks different with each of the different forms. Now you asked a little bit about, well, what if we place that x with a 3? Where does the name go? What's the name now? What ties all this together is the concept of place value. I'm sure some of you are thinking, I see numbers all the time that don't have a name on them, and I work with them just fine. Well, I know this is a simple concept, but it has, just like the idea of a number, has some deeper meanings that a lot of people sometimes miss. So let's start at the end here. What's this last place value? The ones, yep. Then it's tens and hundreds. And those are actually the only 3 place values. And they're repeated over and over again. Ones, tens, hundreds. Ones, tens, hundreds, and so on. Now this first set here is what we call the base group. This next group is the thousands group. Next is the millions. Then it's the billions, the trillions, the quadrillions, quintillions, and so on. In real life, if you ever go much above a billion, you don't need, you can hire somebody else to do your math. I'm not going to insult you by going over how to pronounce numbers, but there are a couple of things with these place values that are important to understand. For example, let's say we have the number 4,726. We're used to seeing the number written like that, but that's not the real number. That's just an abbreviation of the number. The full form, or the true form of that number, looks like this. 4 1,000s, or just 4,000s, and 700s, and 2 10s and 6 1s. Now, some of you may have heard this called expanded form of the number, and it kind of is. It's really just the full form of the number without abbreviating it. When a number is written out in this form, you can see that each digit has a count and a name. This is not just a 7, it's 7 hundredths. This is not just a 2, it's 2 tens. And each of those digits behaves accordingly with our regular operations, which we'll look at more on Thursday. The other thing I want to point out is a situation that arises like this. We might have 2 thousands and 9 tens and 4 ones. What's missing there? There's no hundreds in there. But when we have it in full form, we don't need it because each value is labeled with its place value, with its name. If we're going to write it in abbreviated form, of course, what do we have to do? We have to put that 0 in there in the hundreds place. Because if we don't have those names written out, the names are implied by the location of each digit in that number. Again, I'm not going to insult you by going over that a whole lot more. But the last major important application of the place values is something like this. Let's say I give you 3,854. And I ask you to round to the nearest 1,000. Now, what's that going to be rounded to the nearest 1,000? 4,000. Most of us know how to do that just fine. Well, the technical meaning of that comes from a number line. In fact, there are a lot of actions in math that relate to the number line. When I'm saying round to the nearest 1,000, what it's saying is I have a number line that is numbered in thousands. And if I put this number, 3,854, on that number line, which would be right about there, which 1,000 is it physically closest to? Yeah, it's nearest to the 4,000. Now, we really do not want to have to draw out a number line every time we round, so there's a shortcut. When we're asked to round to the nearest 1,000, the first thing we do is we have to locate the digit that's in the thousands place, which is the 3. What that 3 is telling us is it is between that 1,000 and the next one. It's between 3,000 and 4,000. Then we look at the next digit, which is the 8. Now, of course, we know 5 is right in the middle. 6, 7, 8, and 9 are closest to the next one up, which is the 4,000 in this case. Since that's an 8, it goes up to 4,000. 1, 2, 3, and 4 would be closer to the next one down, which is the 3,000. So that tells us. Now, the only issue comes in what if that next digit is a 5? What if we still have our 3,854, but I ask you to round to the nearest 100? I mean, we locate that 8, right? That's our hundreds digit. We look after that, and there's a 5 there. Now, some people say look at the next digit. I mean, that's not necessarily true. We only ever look at the 2. We look at the one that's in the place we're rounding to, and then the one immediately after it. But this is saying the 8 is telling us we're between 3,800 and 3,900. Right in the middle there is the 5, right? But that's not just 5, it's 54. We've always been told if that next digit is a 5, what do we do? You just round it up. And the reason is, it's not really right in the middle. There's stuff after the 5 that means we're slightly past the middle anyway. So it really is closer to the next one up. The only way it would be a problem is if this was exactly 3,850. Then it really is exactly in the middle. What do? We still round it up. Everything we do in this class, if that next digit is a 5, we're going to round it up. And 99% of your life, if that next digit is a 5, you're going to round it up. I do want to warn you that there are some applications in precision machining and even some precision welding, mechanical design, mechanical engineering, and stuff like that. There are some applications where you got to be careful with that. Like, let's say you have some dimensions like this, where this is 25 millimeters, this is 45 millimeters, it's 15 millimeters, and you need to round everything to the nearest 10 millimeters. Well, these would all round up. This would be 30, 50, and 20. If you had to add those together, you've got 100 millimeters here, where your real total was only 85. You've drastically changed it. That's a huge difference, yes. Now this is, normally we'd be looking at decimals if we're rounding off measurements, but we haven't talked about decimals yet, so I left it this way. So when we get into some precision, I said, mechanical design, precision machining, there are some cases where we round some 5s up and some down. I'm not going to talk about that in here because I don't want to confuse you. But if it's something you're really interested in, let me know and I'll show you. This, if you're ever out there in the field and you see something that's rounded and it's a 5 in that next digit and they rounded it down, just be aware that there are some times when they do round them down. Just to keep those, it's called an error buildup. One last thing, since we talked about number lines, I want to show you this. A little bit unrelated, but we mentioned number lines. Have you seen problems like this where they ask you, put the appropriate symbol in there, equals, less than, greater than? What's going to go in there? The less than, because the 3 is smaller, right? How do you remember which one's which? Well, you probably taught all sorts of weird little... The alligator eats the bigger animal, right? Yeah, that's the one I was just going to say. Where that symbol actually comes from is this. On the number line, what it's asking us is, what side is the 3 on compared to the 11? That side, right? What's that arrow? What's that end of the number line look like? That's what that symbol is just the arrowhead at the end of the number line. That's where it came from. Okay, enough of that. Normally I will not lecture right up to the end of the hour like this. This class is 3 hours a week, but it's 2 credits, which means I'm supposed to lecture for about 2 hours and give you about an hour of guided homework. Normally the lecture will only go up to about 3:05, 3:10, and you'll have that last 10 or 15 minutes to get started on your homework. Today there is no homework, so you don't need work time. I will see you all on Thursday. Thursday's class will be more structured with a little bit more work time in it. Have a good day.